This is the first part of a three-part video. In this part I will talk about psychiatric diagnosis and neuroscience. Today we have a diagnostic system in psychiatry which is descriptive. Descriptive meaning that it is composed of signs and symptoms, and unlike in other parts of medicine where you have an etiological diagnostic system, etiological diagnostic system tells you what went wrong actually and what is the cause of the disease. For example, if you say mitral valve prolapse, then mitral valve is a place in the body and what happened to it. If you say appendicitis, appendix is a place in the body and what happened to it and what needs correction. This type of diagnosis tells you what went wrong, where to go, what to look for, and what to correct. But when you say depression or you say anxiety, is that a place in the body? Is that any kind of mechanism that tells you how to treat? This is why it is very critical that in the future we should have an etiopathological diagnostic system for psychiatry, because today we don't really know how to effectively correct the disorders. So looking for etiopathological psychiatric diagnosis, many years have been invested in trying to find what was called a biological marker, a gene, a neurotransmitter, some kind of alternation at the molecular or cellular level, which will be related to the mental phenomena that we are investigating. But this kind of research has not yielded any real effective advancement in psychiatry. And in my mind, this is because we are ignoring the intermediate level, the level of the whole brain network organization, which is the intermediate level between the gene level and whole brain phenomenology level. Actually, intuitively, one can think that a healthy, asymptomatic subject would be one that has an effective, optimal, well-functioning brain organization, neural network, brain organization. And mental disorders in their various forms, phenomenological forms, would be various types of disturbances to that complex, optimal brain organization. And in recent years, we see more and more of such correlations. For example, maybe the one that is most repeatedly being found in publications is disconnection dynamics. Disconnection dynamics has been related to psychosis. Now, in order to advance in this direction, we should become actually experts in complex system theories, because the brain is actually a physical complex system. Now, how do we advance in this direction? First, we have to solve the psychophysics problem. How come a mental phenomena like mood and awareness, consciousness, is expressed in the brain? Well, the idea of emergent property gives us a reasonable answer. The emergent property is a property of the whole system which is not part of the elements. So if we go to a gene level, molecular level, and we look at a neurotransmitter or a neuron, or even a group of neurons, we don't see that they have characteristics like mood, personality, awareness, and so on. But if we look at the whole brain as a system, it has such properties. And it's not reductive. It's not reduction, because actually if we go deeper, and I will not do it in this video, we need to have a complex nonlinear system. Nonlinear system has additional properties compared to a linear system. So emergent properties would be actually emergent from complex nonlinear interactions in the brain. Now, if we go further, we know that the brain is organized as an hierarchical system. Hierarchy means that we have unimodal simple processors which integrate into multiple more complex processors, multimodal. For example, unimodal would be auditory and visual, but we experience the world with an integration of auditory visual experience, so we have multimodal integration. And then all the multimodal integrations will integrate into one whole brain, constant, coherent brain organization. So this was described by Mashulam when he used the terms of unimodal, multimodal, and transmodal organization. Unimodal being the different modalities in the primary processing units of the brain, and then we have associative brain regions which create the multimodal integration, and then we have whole brain integration, which probably relates to massively interconnected systems like the prefrontal, medial, hippocampal, and so on. Those are responsible for whole brain integration. If we go further, we know that the brain as a complex system has stability. The connectivity could be balanced between disconnection and overconnection dynamics. We need disconnection in order for the brain to be flexible and changeable, and we need connectivity in order to stabilize information and stabilize the structure. Connectivity is also very important in the sense of embedding information. We know that memories are embedded in the brain by strengthening of connection. This is according to Hebbian algorithm. Donald Hebb said that if we have neurons that fire together, the connection between them is strengthened. If neurons don't fire together for a long time, the connection is weakened. But the opposite of this is also correct. If you have strong connections between units, they will tend to statistically activate each other. So you can actually represent information by activating groups of neurons by strengthening the connections between these neural ensembles. These are also called Hebbian ensembles. So actually the brain can achieve embedment of complex information. Actually we have an internal model in the brain of our experience and of our outer world, psychosocial and physical experience. So we now know the importance of connectivity, and we know and we can see that connectivity is shaped by experience. This is another term that is related to Hebb, which is called experience-dependent plasticity. Our experience shapes the embedment of information and internal representations according to the experience. What we know about the brain also is that at each instant the brain achieves whole brain integration, which represents consciousness. This is well described by Bernard Bars, who described global workspace dynamics responsible for conscious experience. Only a whole brain organization can achieve consciousness. And each moment we have a different organization, so we experience consciousness as serial, in the sense that in one instant we have one organization related to one conscious experience and so on. The other one, the next one, and so on. Giulio Tononi was effectively described a whole brain organization in terms of entropy measurements, because when we have one state out of many, then entropy is very low, and actually he managed to extract that from brain imaging and show that when you have conscious experience, then entropy measurements are very low. Now, in recent years we also know that the brain achieves its capacity for optimal organization and optimal functioning by generating a special organization which is called small world network organization. In small world network organization you have many units which are nearby, they are highly connected, and units which are far away are sparsely connected. So you have a balance between density of connectivity in nearby units, which is called clustering, and far away units are less connected, which is called also path lengths. So this balance is very relevant to the structure and the integration of the system, and actually a system that has less clustering can become random and unstable, while that has too many connections can become too stable or freeze or limited or biased. So small world network parameters today can be extracted from imaging data and can give us information about to what extent the nervous system is actually functioning in an optimal way. So now when we know all these types of optimal brain organization, we can begin and hypothesize that different mental disorders, different patterns of phenomenology in mental disorders could be mapped on or related to different types of disturbance or collapse of this optimal organization. For example, if we have disconnection dynamics where many units are loosely connected and many activations are statistically independent from each other, then we can conceptualize, for example, fragmentation of consciousness, fragmentation of conscious experience like we find in psychosis. For example, if the auditory system and the speech interpreting systems act statistically independent in the brain, that are disconnected from visual system, for example, then what we will receive is an experience of auditory hallucinations where someone will have the experience of hearing people talking while visual system is disconnected and you cannot see anyone, which relates to that voice. If we assume that conceptual memories are activated in a connectivity manner, in an associative connectivity manner, then if we have a disconnected system, we'll have activations which are statistically independent, and we'll have loosening of those memories, loosening of those concepts, and loosening of associations, which is very typical to psychosis, for example. So this is just one example of how we can now start and systematically try to map different clinical phenomenology to different disturbances of brain organization. That would be the etiology of such disorders. And it will also be very powerful because it could be validated by imaging, and even more powerful because once we know the algorithm of disturbance, then we can go ahead and plan what type of intervention would be optimal in order to correct it. And the technology for correcting mental activity by controlling neural network activity is becoming available in optogenetics, the deep brain stimulation, and other technologies.